9.5. Last lesson of the chapter. We're ready. Every time you see the word proof, you cringe, right? It's such a cringy word. Proofs. See? Proof by mathematical induction. It's actually a little confusing at first, but then once you get the hang of it, it's like they all do the same thing and you do it over and over. Has anyone ever done this before? Mathematical induction? No? Okay. Okay. Math induction, this is what it is. It recognizes a pattern, and then what it does is it proves that it's true for all the terms. So for example, if I took the sum of the odd numbers, the sum of one odd number is 1. The sum of two odd numbers would be 1 plus 3, which is 4. The sum of three odd numbers would be 1 plus 3 plus 5 is 9. The sum of four odd numbers is 1 plus 3 plus 5 plus 7 is 16.
Whoa, they do that?
They do.
Whoa.
Okay. Does anyone else see what they do? Do you see these numbers over here? 1 and 1, 2 and 4, 3 and 9, 4 and 16. So we can, yes, we can say that the sum of odd numbers, 1 plus 3 plus ... all the way to 2n minus 1, because that's what odd numbers are, they're arithmetic and that's their explicit formula, is equal to the number of terms you're adding up squared. Okay? Now, here's the thing though. I can't just say, yeah, it works for the first 4, so it must work for all of them, proof. No, because actually there's a famous theorem. Have you ever heard of Fermat? Mathematician Fermat? No? No? Or Fermo? I don't know. Some people say Fermo. I've always said Fermat. He said that if you took 2 to the 2 to the n plus 1, that it was a prime number. And you know what? He was right. He was right when n was 0, 1, 2, and 3. But as soon as you got to the fifth number, it actually was not prime. And he said it was true for all, and he tried to prove it, and he never could because it wasn't true. Euler came around in the 1700s. You know what that fifth number was? They call them Fermat's numbers or whatever. 4,294,967,297. And Euler came over, and you know what he did? He factored that. He said, nope, that's 641 times 6,700,417. It's not prime. He did that in the 1700s. Isn't that crazy? Euler did. Anyways, he proved that that wasn't true. So here's what I'm trying to say. You're like, okay, why are we talking about something that's not true? In order for something to be true, if I want to come up with this and I say that this is true, I have to prove it true for all numbers. Well, how am I going to do that? I'm not a computer. I can't spit out all the numbers that are going to work. So here's what mathematical induction does. You are going to prove that it's true for k plus 1 numbers. Okay? If you say this is true for k plus 1 numbers, then that means it's true for the one after that, and it's true for all of them. And so if you prove k plus 1, I could say k is 10, but I proved 10 plus 1. I could say k is 100, but I proved 100 plus 1. So I proved the one after the one you say it goes up to. Do you understand that? So that's what we're going to do for mathematical induction. Now, this is what you do. You have to do 3 things for mathematical induction. Okay? Here they are, and they're called stuff. So, proof, there are 3 steps. The first 2 steps are super easy. Okay? The first step is called the anchor. So step number 1 is the anchor. And the anchor is that you have to prove or you have to show that your formula works for n equals 1. Okay? That's easy. Like that last one, s sub 1 equals 1. I just have to show that the first number, it actually works. The formula works for the first number. Step number 2. Step number 2 is called the inductive hypothesis. Very fancy words here. Oops. The inductive hypothesis. Okay? And in this step, what you do is you're going to get a formula in terms of n, and you can't say that, you can't assume that something's true that you're trying to prove. It's not allowed in math. So you let n equal k instead. It's tricky, right? That's like, you're allowed to do that? Sure. I'm not allowed to assume that n's true, but I can assume that k is true instead. Okay? All right. And then finally, step number 3 is called the inductive step. The inductive step, this is the hardest step. And this is where you are going to prove that k plus 1 is true. Okay? Now that I've thoroughly confused you, am I right? Let's do some. All right. We're just going to jump right in. Are you ready? Let's do it. Okay, number 1. So let's go ahead and we're going to prove what we just talked about. We're going to prove that the sum of the numbers, the odd numbers, 1 plus 3 plus 5 plus 2n minus 1 is equal to n squared. We're going to prove that for all the numbers in the whole wide world. All right, we showed that it was true for the first, what, 4? It worked for 4. If we did the sum of the first 5 numbers, it would be 25, so on and so forth. Okay, so here we go. Step number 1. Step number 1 is you have to show that it works for the first number, okay? So the sum of one number is 1. And then when I go over here and I let n equal 1, I square it and I get 1 also. So I just showed that, yep, it works for the first number. 1 equals 1. Okay, we actually showed it was true for 4 numbers. That was overkill. All you have to do is show it's true for 1 number. Okay, step number 2. You're going to love this step. You are going to assume true. You're going to assume that this formula works not for n numbers. You're not allowed to assume that's true. That's what we're trying to prove. But you're going to assume that it's true for k numbers. Okay? So we have 1 plus 3 plus 5 plus ... 2k minus 1 equals k squared. I'm going to assume that that's true. So maybe I'm trying to prove it for n numbers, like maybe n's a million. But I say, okay, I'm going to say, well, it's true up to a certain point of k. K is the amount that it's true till. All right, so I assume that that's true. Step number 3. Now we need to prove, yeah.
What's the difference between n and k?
Yeah, so n is what we're trying to prove. K is going to be a number smaller than n that I'm saying that it's true up to that point. Okay, so you're not allowed to assume true for n because that's what we're trying to prove. All right, now here comes the last step, and this is the hard step. We need to now show that k plus 1 works. Okay? And here's how you show it. This is for k numbers. Okay? Now I'm going to write this for k plus 1 numbers. So I'll show you what k plus 1 numbers looks like. It's 1 plus 3 plus 5 all the way to 2k minus 1. And now I'm going to add on the next term. See, this right here is for k amount of numbers, and now I'm adding on the next one. And the next one is going to be 2k plus 1 minus 1. Do you see where I'm getting that? I'll show you. This right here is the kth term. Kth term. This right here is the k plus 1 term. I took this k and I replaced it with k plus 1. So that's the next term, okay? Now, since this is going to now equal k plus 1 squared. If I'm adding up k numbers, it equals k squared. If I'm adding up k plus 1 numbers, now it's going to equal k plus 1 squared. So on this side, I replace k with k plus 1 also. Okay, so now here comes the work. Those steps you're going to do every single time. The work is I have to show that this side equals this side. I have to show that. Are you nervous? A little bit? All right, so here we go. Let me show you how to do that. Do you see this whole thing right here? Go back to step 2. What did we say that was equal to? K squared. That's why we do that in step 2. We say this entire thing is equal to k squared. So let's substitute that in. K squared plus. Over here, let's simplify this. This is 2k plus 2 minus 1. We're going to try and show that it's equal to k plus 1 squared. Now, the thing about proofs is there is a line right here that you cannot cross. If I'm trying to prove this side equals that side, I'm not allowed to subtract. It's not an equation. I'm not allowed to do unto one side as I do unto the other. I'm not allowed to add 1 to this side. I'm only allowed to work with this side or that side separately and show they're equal at the end. Okay? So let's do it. This right here is k squared plus 2k plus 1. And now it's your option. You can either factor this or you can FOIL that. I'm going to factor this. This is what times what's 1 adds up to 2 would be k plus 1 times k plus 1. And I just showed that these sides are equal, and then you're done. It's proved. Whew. It's hard the first one you see. It is. Did you follow it okay, though? No. Sam, do you love it? Yes. What? Is he lying to me? Jeanette, is Sam lying to me?
Yeah, he always lies.
Yeah. Okay. Let's do another one. Number 2. All right, number 2. Aren't these so good? No, it's all right. I get it. All right, we're going to prove a bigger formula now. Are you ready for it? We're going to prove that the sum of these numbers, 1 squared plus 2 squared plus 3 squared. So we're adding up the squares to n squared is equal to, we're going to add up these. This is equal to n times n plus 1 times 2n plus 1 all over 6. Who comes up with the formula? That's what I want to know, right? Do they see a pattern and they just try the formula and now you have to prove it? I don't know. It's pretty cool. So if I were to add up the first 3 perfect squares, 1 plus 4 plus 9, I could plug in n equals 3 over here and that would tell me what it's equal to. That's the formula. Okay? All right, so here we go. Step number 1, we have to show that the first one works. The sum of the first perfect square is 1 squared, which is 1. Now I know my 2 examples they've given you have both been 1. It doesn't have to be 1. It just so happens that it's 1 here. All right, so now let's go ahead and plug in n equals 1 over here because we're adding up one number. And so when I plug in 1, I get 1 times 1 plus 1, which is 2, times 2 plus 1, which is 3, over 6. And I get 6 over 6, which is 1. So I just showed that the first number works. You could show the sum of 2 numbers works if you want to. You don't have to. The sum of the first 2 numbers would be 5, right? 2 squared is 4, plus 1 squared is 5. And if I plug in 2 into here, I'll get 5. It'll work. It works for all of them. By the way, I'll never ask you to prove something that's false. That would be really, really awful. Okay, so step number 2. Write these words down. Assume true. Those are very important words. If you just write down, the whole thing in terms of k, I don't know what you're saying. But we're going to assume that this formula is true for k numbers. So 1 squared plus 2 squared plus 3 squared to k squared equals k times k plus 1 times 2k plus 1 all over 6. So you just basically, the first two steps are pretty basic. They're pretty easy. Show the first one works. The second step is to assume true for some number k. You just rewrite the entire thing in terms of k instead of n. All right, here comes the hard stuff. Here we go. We are going to now prove k plus 1. Okay, so here's what you do. You want to write this all the way out to k terms. So 1 squared plus 2 squared plus 3 squared plus k squared. So you rewrite everything that you see right here. And now you're going to add the next term on. The next term is the k plus 1 term. So this is going to be k plus 1 squared. And this is going to equal. Now, all of this up here, this entire side right here, this is all in terms of k, but now we've added k plus 1 terms. So I have to change all those k's to k plus 1. So the first k is k plus 1. This one is k plus 1 plus 1. Do you want to just write k plus 2? Okay. The next one is 2 times k plus 1 plus 1 all over 6. Okay? So in the third step, you write down the k numbers. Then you write down the next term, the one that you're adding onto it, and then you write the whole thing in k plus 1 now. All right, so now we're ready to substitute. This entire thing right here, we assume true, it was equal to that. So let's go ahead and plug it in. So I get k times k plus 1 times 2k plus 1 all over 6 plus this green part right here. K plus 1 squared is equal to this entire side. So let's clean this up. I've got a k plus 1, a k plus 2. This is 2k plus 3. Yeah? Distribute the 2. 2k plus 2 plus 1 is 2k plus 3 all over 6. Okay. Now, my job is to show, now don't forget there's a wall here. My job is to show that the left side equals the right side. It will. It does. It has to. I'm proving something that's true. Okay? But I have to show that this equals that. Yikes. How are we going to do that? It's called algebra, but it's really hard algebra. All right, so here we go. Do you notice this side? Everything's all over 6. So let's get a common denominator here. So I have k times k plus 1 times 2k plus 1 over 6 plus, and I'm going to multiply this term top and bottom by 6 to get a common denominator. Yes? So far so good? All I did was take this k plus 1 squared and multiply it top and bottom by 6 to get a common denominator so I can add these together. I'm ignoring the right side for right now. Okay? All right, over here I get k times k plus 1 times 2k plus 1 plus k plus 1 squared all over 6. Okay, so now I have one fraction. That's nice. But it still doesn't look like the other side yet. Now you can do a couple of things here. One, you're probably looking at this going, am I really going to have to FOIL all that crap out? That's what you're saying, huh? You're saying that? Yeah.
Don't you have to have the 6k plus 1 squared?
Whoopsie woo-woos. Thank you. Nice. I saw some of you looking up there like, what's going on? I knew I made a mistake. Yes. Okay, but you're probably thinking, do I have to FOIL this whole stuff out, FOIL that whole stuff out, FOIL the whole side over here? And that is one way to do it. That is a horrible way to do it. What I'm going to do is I'm going to look at this side over here, and these, see how there's two terms up top? And they have a common denominator, or a common factor. They each have a k plus 1. And I'm going to take that k plus 1, and I'm going to factor it out to the front. Okay? Are you ready? Let's do that. It's actually a shortcut, and it works really, really nicely. So we're going to take a k plus 1 out to the front. And when I take a k plus 1 out to the front, I'm left with k times 2k plus 1. Okay, that comes from the first term. That comes from here. K times 2k plus 1. And then what else am I left with? Plus 6 times k plus 1. Very good. All over 6. Okay? So over here, I have k plus 1 squared. I took one of them out, and I'm left with just one of them now. So now, let's keep that k plus 1 out front, and let's simplify all the stuff inside. So I get 2k squared plus k plus 6k plus 6 all over 6. This is k plus 1. This is 2k squared plus 7k plus 6, bless you, all over 6. And then you want to factor that any way you can, but you can kind of cheat a little bit. I mean, I don't want to tell you this, but oops. You can kind of look over at the other side. Like, what are we trying to get this whole thing equal to? We're trying to get it equal to, it's way back there, k plus 1 times k plus 2 times 2k plus 3 all over 6. Well, guess what? I have this k plus 1 that matches. Do you know what this factors as? It factors as this. I can see it, it's right there. So this is going to factor as k plus 2 times 2k plus 3 all over 6, and it's equal, and we've proved it. Whew. It's the algebra that's the hard part, huh? Yeah. You could have also, if you didn't want to factor, you could have stopped at this point, gone over here, and FOILed that out, and it would have been that, and that would have been fine too. As long as this side equals that side by not doing something to both sides. All right, I'm just going to do one with you, and then I'm going to cut you loose. I know that's not a lot, but I want to see if you can do them. So your homework is 1 through 4, 10 and 13, and then on a separate piece of paper, you can choose, or not to choose, numbers 14 and 15. You have to get them right to get the extra credit bonus. Those are going to be worth 2 points each. And they're a little tricky. They are. Okay? All right, so let's do number 1 together. Let's do number 1. We're going to prove that if I add up the evens, 2, 4, 6, 8, all the way to 2n, that is going to equal n squared plus n. Okay? Now this one's not as hard. That last one with all the fractions and the factors, that one was hard. This one's not that bad. But make sure you show all 3 steps. So let's do the anchor first. The anchor is to sum up one number. What's the sum of one number? 2. It's 2 this time. I'm glad I'm doing this one with you because it's been 1 the first other times, you know? But if I add up the first number in this series, it's just 2. The first number. So now we'll plug in, and you're not plugging 2 in over here. N stands for how many numbers you're adding up. You always plug in n equals 1 over here. When I plug in n equals 1, I get 1 squared plus 1, which equals 2. So these are equal to each other. I just showed that this works for the sum of one number. Sum of one number is 2. I plug in 1 over here. I get 2. It works. Okay? All right, step number 2. Assume true. I know this always felt weird to me when I would do proofs. Like, what's the difference between n and k, right? I know. But you're not allowed to, whatever you're proving, you're not allowed to assume that it's true. So we get around it by saying instead of proving or assuming it's true for n numbers, I'm going to assume it's true for k numbers. That's not the same. Like, but it is. But it's not. K squared plus k. Sam hates it. Sam, you're such a hater. Okay, number 3. Right, Jeanette? Seriously. Oh. Sam, do your other teachers pick on you as much as I do? No, that's good. Okay. Number 3, here we go. They just don't like you as much as I do, seriously. Now, we have to prove that k plus 1 numbers work. If I'm proving that k plus 1 numbers work, that means that all the numbers work. Because you could say, no, k is 100. Well, I just proved 101. It's always the one after. See? That's what we're doing here. All right, so let's do it. Add up the numbers to k. Okay, there's the numbers to k. Now we're going to add on the next number, the k plus 1 term. If I add on the k plus 1 term, it's 2 times k plus 1 on that side. And this is supposed to equal, do you know what this is supposed to equal? K plus 1 squared plus k plus 1. Okay, basically on this step, anywhere you see this 2k, I made it 2k plus 1. These k's, I made them k plus 1s because it's one more. You're adding on the next one. Okay, now we're going to substitute. This entire thing here, we said was equal to k squared plus k. You got it! Yay! Yes, good. I'm glad we're doing this. Okay, this entire series here, 2 plus 4 plus 6 plus 8, all these dots in the middle, all the way to 2k, we said was equal to k squared plus k. And then I have to add that to 2k plus 2. And I'm saying that this is equal to k plus 1 squared plus k plus 1. Okay, now this next part is up to you. And by the way, if you look in the back of the book for answers, it will say they will vary. Answers will vary. Because they do. Because I could choose to go over here and factor this. You could choose to come over here and FOIL that. And we're both right. Whatever you do, you work on one side and you get to a point where you can't go anymore, like this. K squared plus 3k plus 2. Maybe I'm terrible at factoring and I don't want to factor that, right? And I'm like, I'm going to go over to the other side now. I'm going to FOIL this guy out. K plus 1 squared is k squared plus 2k plus 1. And then I still have plus k plus 1. If I combine those together, I get k squared. I have 2k and k. That makes 3k. I have a 1 and another 1. That makes 2. And as long as at the very end my two things equal each other, I've proved it. Okay? See, over here someone could have said, no, I'm going to factor this. Say that that's k plus 2 times k plus 1, and then do that and whatever. You can do it a different way.